We are now asked to solve this non-homogeneous differential equation, and we'll notice that we've added another detail here. It's an initial value problem, and we're going to see there's a second wrinkle that turns up along the way. But that'll become obvious as we go through the solution. So, when we have something like this, we try to do the easy part first, which is the complementary solution, and that is going to be found as the solution to the corresponding homogeneous differential equation. Same left-hand side, but the right-hand side is just 0. That we know how to solve. We go to the r's, and we get a 1 there, and there's no r because there's no first derivative. That's the difference of squares, so we can factor as r plus 1, r minus 1, and we get r equals -1 and +1. So our corresponding solution to the homogeneous equation is going to be c1 e to the negative x plus c2 e to the x. That's handy, we have that in the bank. Next step is to find the y solution that corresponds to the non-homogeneous part. Let's base ourselves on the right-hand side. And when we look at the right-hand side, we notice that the differential family would be the set of functions that we need to build the right-hand side or its derivatives. And a set for that would simply be e to the x, e to the negative x, and the constant 1. With those three functions, we can build our right-hand side. And even if we take derivatives, we're only going to get the same kinds of functions back. However, we do have a difficulty. You'll notice that these two functions here overlap. They're already present in the complementary solution. What that means is that if we sub those in to the dE, we're going to get a whole bunch of stuff that equals 0. Why do we know that? Well, we know e to the negative x is a solution to the complementary homogeneous version. So literally, if we plug it in, we get 0. There's no way we can plug it in and get an e to the x back out. It's not going to happen. Well, fortunately, that might seem like a showstopper, but we have seen exactly the same problem before. What we need to do is multiply any overlapping functions by, well, what happened when we had repeated roots and had the same exponential twice? We multiplied one of them by x. Now, there's a general rule here you might see in some practice problems, but you keep multiplying by x until you get something different. So there's two key things. Multiply by x as much as you need to get a new function, but only do it for the overlapping ones. E to the x is already in our complementary solution. E to the negative x is already there, but our constant is not. And so that means that our non-homogeneous solution is going to look like x e to the x. It's going to have another building block of x e to the negative x, but it's also going to have a third value, c times 1, that is not multiplied by x. That is a very important point if you want to avoid spurious calculations and trying solutions that simply are not going to be solutions. So, two of them overlap, the e to the x, e to the negative x, those get bumped up by that x factor. The last part of our differential family is a constant or 1. We do not bump it up because it does not overlap with what we found so far. If that makes sense, and again, we're arguing by analogy, we can prove it more rigorously, but that doesn't tend to help most students in terms of understanding the process. We now have a proposed solution to our non-homogeneous equation. Let's go ahead and sub it in. If we need to sub that into our differential equation, we're going to need a second derivative of that. Well, we can't go straight to that. Let's take one derivative at a time. The derivative of the first term is a product rule, e to the x plus x e to the x. Derivative of the second term is an e to the negative x minus x e to the negative x. And the derivative of the third term is just 0. The second derivative will be an a e to the x. Derivative of this, again, is a product rule, another e to the x plus an x e to the x plus b, same idea, negative e to the negative x. And differentiate the second term, we'll have negative, the x goes away, e to the negative x minus x e to the negative x, close bracket, close bracket. And that can get tidied up a little bit. 2 e to the x's plus an x e to the x. And we'll have a b minus 2 e to the negative x's plus x e to the negative x. Perfect. We now have the ingredients we can try to sub in to the differential equation to see if we can solve for a, b, and c. In this situation, we have a whole bunch of terms and we have a whole bunch of functions. In fact, we have too many functions running around right now. So let's just do this explicitly and work our way through it carefully. So we're going to put those into the differential equation, which means we'll have an a. I'm going to break every term up into pieces so we can look at the coefficients one by one and see what we get. So this is all y double prime. That is all y double prime minus y. Well, y is up here, a x e to the negative x plus b x e to the negative x plus c, and that has to equal, sorry, that's y, then that has to equal e to the x minus e to the minus x plus 2. Now, there are 5 different functions running around. There's 1, 2, and 3, but there's also the x e to the x's and x e to the negative x's. However, if we take a careful look at 2 of those, oh look, a x e to the x. That's the only term here that has x e to the x. Oh wait, typo in fact. This is actually a good sign. X e to the x is what that should be. Let's erase that. So a x e to the x minus a x e to the x, those cancel. Next, x e to the negative x. We have b of them here, and we have minus b of them. Those cancel. And now we are down to 2a e to the x's minus 2b's e to the negative x's minus c equals e to the x minus e to the minus x plus 2. Now we have 3 functions that are being worked with here, and we have 3 unknowns, the a, b, and c. This is actually a fairly simple case here. It's complicated leading up to it, but simple here. If we equate the coefficients, well, 2a has to equal, how many e to the x's do we have on the right? We have 1. So 2a has to equal 1, and so a must be a half. When we equate the coefficients of the e to the negative x part, we would have negative 2b's of those on the left, and that would equal negative 1 on the right, so b is also equal to 1/2. And last but not least, for the constant terms, we have c equals 2, negative c equals 2, so c is equal to negative 2. And there we are. A, b, and c, those are the 3 undetermined coefficients in our non-homogeneous solution. So we can write down our general solution right now as y equals, from the first page, c1 e to the x plus c2 e to the negative x plus, okay, that was our complementary yc solution, plus what we just found, a, b, and c in these terms, 1/2 x e to the x plus another half x e to the negative x minus 2. This all together is our non-homogeneous part of the solution. And that would be our general solution. Notice that all functions here, all 5 of them, e to the x, e to the negative x, x e to the x, x e to the negative x, and constants 2, are linearly independent. The biggest warning sign in looking at a solution here is to see duplication in the solutions, or nonlinear independence. If we see that, that's a really big red flag. So if we are tempted to have linearly dependent solutions, we do the same fix we did earlier, we apply it here as well. We multiply the conflicting or the overlapping functions by x until they become non-overlapping. And that's the bulk of the work in terms of the ideas. Last but not least though, this is an initial value problem. So we also need to solve for C1, C2. Hopefully that'll be straightforward here. Having copied down our solution, we now solve for C1, C2 using the initial conditions. So if y of 0 equals 0, then that means that 0 equals all the e to the zeros are 1s, and x's as a multiplier give us zeros. So we just get c1 plus c2 and minus 2 at the end. Or c1 plus c2 equals 2. For the y prime of 0 equals 0, we need y prime. And we need y prime of this entire beast here, so let's go ahead and calculate the derivative. There's our derivative using the product rule for the two terms of the x e to the x types, and the derivative of the negative 2 is simply 0. Then we sub in our 0 equals this at the time 0. Again, any x times is going to disappear, so we simply end up with c1 minus c2. We do end up with some different constants now. We have plus a half and plus another half. So c1 minus c2 is going to equal negative 1. All right, almost done. We have two equations here. You can do whatever you like to combine them. I would simply take this one, let's call it 1 and 2 here, and do 1 minus 2. The c1's cancel. We get c2 minus minus 2 is 2 c2's. Equals 2 minus 1 is 3. c2 is 3 halves. And then c1 would be 2 minus c2. 2 minus 3 halves is positive 1 half. And lo and behold, we end up with 1 half e to the x. So what are we doing? We're filling in the general solution down to the constant c1, c2. Plus 3 halves e to the negative x, plus 1 half x e to the x, plus another half x e to the negative x, minus 2. And that is our particular solution. To the initial value problem. So once we get down to knowing where we start, second order where we start, and the velocity or rate of change, then the complete solution we can generate has all the constants filled in and is sometimes quite a complicated beast like this. But the process of finding the complementary solution, which is the solution to the right-hand side equals 0 version of the equation, building our solution to the non-homogeneous part, and being careful about defining the building blocks in that function, using the initial values, then to solve for the c1, c2 in the corresponding or complementary solution, and putting it all together to get the overall solution. That's the entire process.